Hello, today we'll be starting with numerical integration. The first method that we will look at is called the trapezoidal method. So this is a way to find out the way to integrate a function using a numerical method. For example, if you have this function defined as given here, right? This is y and this is x. Uh, this function, let us say it is defined by some function f of x, right? I can call this f of x. So a way to integrate would be to simply, if you know what this function is, and if the function is simple enough, you can find out the integration of this simply by using your rules for integration, wherein you integrate a function from limit a to b. That can be done if the function is simple enough, right? If you have a very simple function like x square or something like that. But numerical integration helps you when you have a complex function for which the analytical way of finding out the integration would be difficult. So that's where the numerical integration helps you. Alright, so what you need to do is figure out uh, a way to calculate this integration numerically between the interval a and b. Okay. Right. So how do we do it using the trapezoidal method? So we divide. We know that the integration of a function is basically the area under the graph, and the area under the curve in this case is the one enclosed by this blue line, the red dashed lines, and the green line, which is in between a and b. So this is the area that we have to find out in order to integrate the function. One of the ways that we can do that is using the trapezoidal method. What we do in that is we draw trapezoids. So for example, if I divide it in one more interval, for example, if I also divide it in this, let me draw this line. I'm sorry. Okay. So now I can think of this area being represented as a sum of these two trapezoids, right? This point is a. What would this point be? This would be f of a. This point would be f of c, and this point would be f of b. How do you find out the area of these trapezoids? So it's simple if you think about it. If you draw a line here, for example, you can see that it is a sum of a rectangle and a triangle. So a very easy way to derive the formula would be this. So what's the area of this rectangle? And yeah, when you're dividing it into intervals, if you're dividing into intervals, you need to know the width of each interval. So for example, I say that the width of my interval here is delta x. Okay, so ideally we want equal intervals in between a and b, equal divisions in between a and b. So how do we calculate the area now? What we do is we find out the area of the rectangle, which is so the integration can be given as the area of the rectangle, which is f of a times delta x plus the area of the triangle. I'm talking about the first one here, this first area, I1, let me call it. So this is half times what's the area of the triangle? It's half times base into height. Base is delta x and height is, if you see carefully, till here it's f of c and here it's f of a. So this much length is f of c minus f of a, right? If you add this up, what you get is, so half of f of a times delta x will get removed from here, so what you will be basically left with will be half times delta x f of a plus f of c. Similarly, if you find out the area of this part, you get I2, similarly calculated as half times delta x f of c plus f of b, right? So the total value of integration would be I equals half of delta x f of a plus 2 times f of c plus f of b. Okay, so this is the general form, or not the general form, this is the numerical, this is the formula if you want to calculate the, if you want to integrate the function numerically using two trapezoids, right? Instead of just two subintervals, if you have n subintervals, then the way you calculate the integration is I equals delta x by 2, the value at the first node, right? Then 2 times sum of, so if you have n subintervals, you would have n nodes, right? Or n points, n plus 1 points, right? Because for example, in this graph, you have two subintervals, this and this. How many points do you have? If you have two intervals, you have 3 points. So if you have n subintervals, you will have n plus 1 points or n plus 1 nodes, right? So you would need to evaluate the function at the first node, then twice the function value at all the interior nodes. So this is the value of the function at all xi, where I goes from not 1, I goes from 2 to n, and then again you evaluate your function at the last node at xn plus 1. Why n plus 1? Because you have n subintervals. For n subintervals, you'll have n plus 1 nodes, right? So this is how you figure out the, or this is how you integrate numerically using the trapezoidal rule. Now let's implement this in Octave. So this time I'll be using the GUI of Octave, because I realize some of you may have problems when looking at the code written in the terminal of Linux. So it's better if I do it using the normal GUI, graphical user interface. Alright. So same thing, there I used to write in Vim editor, here I'll be using this editor. Let me first go to where I write all my codes. So cd, same commands work here. I need to change my directory to graduate computations. In fact, I need to make a directory there which is numerical integration. Okay, so now let's go to that numerical integration, and here I'll be writing my code. So let me open up a file, edit, let me call it trapezoidal.m. It's asking me to create it. Yes, I will create it. Okay, so it has created a function with that name. I don't want that. So what I'll do is I'll just create a file from here itself. Let me delete what I've created, and I'll, yes. So let's, in order to create a new file, don't write edit. What you do is go to editor and just click on this new file, new script. And again, as we start all the time, clear CLC and close all. Okay, now what do we, let us save it, right? Before we do anything, let us save this with the name trapezoidal.m. trapezoidal.m. Fine. Okay, so let's choose a function. Let's choose a function f. Let this function should be going to 2 raised to x. If you want to see how this function looks like, you can always, see the query points 0, 0 0.01, 100, maybe 10, and plot the function at all these query points, right? And let's run it. So this is how the function looks like. We need to find the area under the graph. Okay, now let's do this quickly. Now we know what a is what do you want to integrate this in between. So let us integrate this function between 0 and uh, between 0 and 1, for example, right? Let us integrate this function between 0 and 10. All right, then let us choose how many subintervals we are going to make. So here we initially had two subintervals, right? So let's start with that. I want two subintervals. So my dx value, delta x value, would be b minus a divided by n. Right, now I need values of all these, right? I need what is a, what is c, what is b. So one way to get that would be using this command, which is start from 0 or start from a, increment by a value dx until I get to b, right? So let us see what this gives us. Let's not plot this for now. Let's me comment this out. This is how you comment. If you put a percentage sign in front of a command, that line will not be read by the editor. Okay, now let's go to the command window. Let's print x. So as you can see, what did the command do? I had a equal to 0, b equal to 10, and dx equal to 5. So when I wrote a dx b, it started with 0, incremented by 5, then again it went to 5, incremented by 5 again, and went to 10, and it stopped. So this is what this command does. You can replace dx by some other value of the interval, and then you will have an array generated between 0 and 10 with values incremented by this dx, which is 2 here. So 0, 2, 4, 6, 8, 10. Okay, so why did we do that? Because we need x values at these points, at a, c, and b. That is why we did this. Now I need the value of the function at these points, so that can be calculated easily enough. Y is equal to f of x. Right, now I need to calculate the integration using this formula. For n sub intervals, I have this formula, right? So what I can do is see, the first one and the last one, they can be added, right? But for the inner parts, I would need to run a loop, because it's not fixed how many intervals I'm going to have. So for the first one and the last one, what I can do is, let me initialize I equal to, I'm just going to add this value and this value. Okay, so let me add these. So what is f of x of 1 plus f of x of n plus 1? So the last value. So the last value is, either you can count or you can simply write x of end. So x of end will give you the last value. If you want to look here, this is x, right? What is the last value? If you type x of end, it will give you the last value. X of 1 gives you the first value. Okay, so f of x of n. So this is done. Now I need to take care of this part. Alright, so for that I run a loop. For I equals, this goes from 2 to n, right? So 2 to n. Let me end it. Okay, what I do is, I equals I plus 2 times f of x of I, right? I'm multiplying it 2, and then I'm adding all these values one by one, wherein I goes from 2 to n. Okay, so let us see what this gives us. Yeah, I forgot one thing. We also need to multiply it by delta x by 2. So I equals dx by 2 times I, and this is the final value of our integration. So let me run it again. Trapezoidal. Let's see what I is. So why is that? What's f of 0? Okay, let me see what mistake I've done. Let me print these values, then I'll come to know where the error is. When I remove the semicolon, it prints the values to the command window. Let me run this. Okay, so now it's giving the correct value. Why wasn't it giving it earlier? Maybe I didn't run that code that time, probably. So yeah. How do we know whether this is correct? So I know the function which I have already defined. I can use the inbuilt mathematical, Octave has an inbuilt function which can integrate functions for you, which is called integral. You need to pass in the function, which is f. You need to pass in the interval, which is a, b. So it's 1475.2.9. So as you can see, this value is quite different from what we got, but remember, we only used 2 subintervals. If we use 50, for example, then we can see what the value is. For 50 subintervals, I is 1478.2, and using MATLAB's own built-in function for integration, I get similar values. But still, it's not very close. So let me increase the number of intervals to, for example, 200, let's say, and then compare. So I is 1476 and this is 1475.9, so quite close, right? If you still want to get closer, maybe increase it to 1000 and check. I is 147.59 and the MATLAB's own integration function gives you 1475.9. So similar now. There's another function in MATLAB. So in fact, you don't need to implement this, but we are doing it for learning purposes. So trapezoidal function is already implemented in MATLAB. What you need to pass to it is the x values and the function values, and then it calculates the integration for you, integral value for you. Okay, so now we have done this. Let us see quickly, let us see a way to implement this in an even better way. We'll use what is called vectorization, right? So what we do is, let me do this using another method called vectorization. This is a general method which can be used in any code that you write in Octave or MATLAB. What it does is, we, instead of writing in loops, we write it in single lines, and you'll see what I mean by that. The advantage of that is that when you write code in such a way, it makes use of MATLAB's optimized functions, and it makes your code really fast. We can see how fast our code will be when I run this. So instead of writing this loop, what I can do is, let me write I2, I have already defined, or IV, right, vectorized integral. So what I can do is, I can write this statement in a single line instead of using loops. So I can write dx by 2 times f of x of 1 plus, what's the in between, is 2 times sum of f of x of I, where I goes from 2 to n. So the way I write that is 2 times sum of f of x of I, where I goes from 2 to n. So 2 to n. So we have n minus 1. So this is n minus 1, right? We have, if n gives you the last value, n minus 1 will give you the second last value, plus f of x of n. So using a single line, we have accomplished what we did using all these lines, right, from here to here. Let us see if I get this value. So there is an error. I think I've given an extra extra bracket at the end, probably. Yeah, that seems to be the error. Let me run it. Okay, let me again go back and check what mistake am I doing here. F of x of 1. Okay, I didn't close this. Okay, let's go back another, and f of x of n, and I would need another bracket here. I guess that should solve our problems. One. So this bracket always confuses me. I'm not sure if I close it, if I close all the brackets or not. So this one is x of 2 to n minus 1 times, okay, I will need another bracket here. So be careful, everyone makes this mistake. So IV, okay, yeah, I is this. What is IV? Same thing, right? So what I calculated using this for loop, I got the same value using the vectorization. But why should we use this? One thing, it looks quite simple, right? It's very simple to implement. You can do it in one line, where you did this in 1, 2, 3, 4, 5, 6 lines. Another way is that, another positive is that this is much faster. So what you can do is, you can run this function called tick and talk. So when you type tick, MATLAB starts counting the time, and when you type talk, it stops its count, and it print outs the time taken by these lines. It prints out the time taken by Octave to run these lines. So let me time these lines, and let me time my vectorized lines and see which one is faster. So as you can see, for the first one it took 0.018 seconds. For the second one it only took 0.001 seconds. So for 1000, as you increase the number of loops, the difference will be quite clear. Now instead of 1000, let us do it for 10,000 and see what the timing is. So as you can see, it's 1.15 seconds now for the loop version, and only 0.000489 for the vectorized version. So I guess you have understood how we can implement this, right? One final thing would be to make my own trapezoidal function. So you already have a trapezoidal function by MATLAB called trapz. Let me make my own. So how do we do that? We start with function. It returns the value of the integral. What do we name the function? Let me call it my trapz. It takes in the function f, a and b, and so I can either end with function, or I can just write end. That would also do. I can just copy this line, right? What else do I need? So I would need n from the user as well. How many intervals, sub intervals do I want? And dx value can be calculated from these inputs, b minus a divided by n, right? And I think this is enough. So this is my function. I need to save it with the same name, and let's see how this works. So let me define a function which is already defined, right? So let me call my function which I have defined now, my trapz. It takes in f, a, so let that be 0, b 10, number of subintervals, let that be 500, and let me run this. So there is a mistake. Why is there a mistake? It says x is undefined. So I didn't define x. That's right, I never defined x. So how do you define x? X was a to b with an interval dx, and now it should work. Let's get back here and run this again, and my function is now working. Let us compare it with MATLAB's function, which is trapz. It takes in f, it takes in 0 and 10, and so it doesn't take that. What it takes in the x and y values. So it takes in x and it takes in f of x, and it returns 1475.9. If you want to know more about a function which is implemented by MATLAB itself, or implemented by Octave, you can just type trapz help and the name of the function, and it tells you how you can use that function. Alright, so I think today we have covered quite a lot of things. So thank you for watching, and I'll be covering another type of numerical integration in the next video. Thank you.